This video is on the objective compute the value of the test statistic using the expected frequencies for a chi-square goodness of fit test. Alright, and this is the second video on this objective. Hopefully you've watched the first one because I'm not going to go over as much in this one. I'm not going to go over the instruction with you. That's in the first video. So let's just get into it. Let's give it the calculator. We'll come back to that. Alright, so again, if you want to see more instruction about this, click on more instruction, look at their videos, their notes, their examples, and hopefully those help you. So here you are comparing some observed data with the expected uniform distribution to see if they are the same, right? So do the observed data fit a uniform distribution? The data appear in the table below. Find the test statistic, right? The chi-squared sub 0 for the chi-square goodness of fit test. Round your answer to 3 decimal places. All right, so I'm going to write this out on a piece of paper, and we'll go over this calculation. Okay, so here's the table that was given. You have these 5 outcomes, 5 categories, and of the people that this person observed, 10 of them belong to category 1, 5 of them belong to category 2, 13 belonged to category 3, 9 of them belong to category 4, and 8 of them belong to category 5. All right, so now these observed counts are the actual data themselves. All right, this represents what actually happened. The expected counts are what you would expect if they fit, or if they really had a uniform distribution. Right? And again, it doesn't have to be the uniform. It's uniform in this example, and also in the first example from the first video on this objective. But it could be any distribution, right? We could expect a set of data to fit some other kind of distribution. And it just so happens that these first couple of examples are dealing with the uniform distribution, right? The same throughout. So look, the number of observations, right? The number of observations in the data is 45, right? 10 plus 5 plus 13 plus 9 plus 8 is 45. And if you were expecting the distribution to be uniform, and there were 45 observations, you'd expect 9 of them in each category, right? 45 divided by 5 is 9. All right. Okay. So now, we're given this table of information. We're asked to calculate the chi-squared, test statistic for a goodness of fit test, right? How well does this observed distribution fit the expected distribution of a uniform distribution? Now they wrote down a formula for you in the problem, right? It was this thing here. The sum over k of the observed values minus their corresponding expected values squared divided by the expected values. Now k here just tells you how many terms are going to be in the sum. Basically, how many of these categories are there? Because you're going to have one term for each category, one term for every observed value and their corresponding expected value. So the value of k here is 5. Again, the value of k is the number of categories, right, or the number of observed and number of expected values. There's 5 each. Alright, so if I do this out by hand, right, for the outcome number 1, category 1, 10 of the observations were in category 1 when, if I assumed it was uniform, I'd expect 9 of them to be in category 1. Right? And so we have 10 minus 9 squared divided by 9. Right? Observed minus expected squared divided by expected. Plus, and then I do for the next category. Category 2, 5 of them were observed to be in category 2. I would expect 9 of them to be if they were truly uniform. Square that and divide by expected 9. Plus And then for the third category, 13 observed minus 9 expected squared divided by expected. Fourth category, fourth outcome, 9 minus 9 squared divided by 9. And then for the fifth category, 8 minus 9 squared divided by 9. Right? Now again, the first two examples I've shown you from video 1 and this video, all the expecteds were the same because we were trying to see how well we fit a uniform distribution. If we were trying to see how well we fit some different distribution, then all these wouldn't be 9 and we'd have different denominators here. So just be aware of that. You could have a goodness of fit test where you're trying to fit some other kind of distribution instead of just the uniform. But uniform's real nice, easy to check. So all these fractions here have a denominator of 9. So I'm going to put the big fraction bar. They're all over 9. And then I'll just add the numerators, right? So 10 minus 9 is 1, squared is 1, plus 5 minus 9 is negative 4, squared is 16. And 13 minus 9 is positive 4, squared is also 16. 9 minus 9 is 0. Right, squared is 0. And then, negative 1 squared is 1. So we're getting here 34 in the numerator, right? 17 plus 17 divided by 9. And you can punch this in a calculator. They're asking us to round this to 3 decimal places. Now this is 3 7/9, so this would be 3.7 repeating. 7777. So to 3 decimal places, this is going to be 3.778. I'll just double check this on the calculator. All right. So we got 34 divided by 9. All right, so my test statistic is 3.778. Now, you could do it this long way, but I did show you in the first video, and I'll show you again here, a couple alternate methods for finding the test statistic in these chi-squared goodness of fit tests. An alternate method was to enter lists. I go stat, edit, and then down list L1, I'll put the observed values, right? There were 10 in the first category, and then 5 in the second category, and 13 observations in the third, and 9 in the fourth, 8 in the fifth, right? And then down list L2, or some other empty list, whatever you decide, I'll put the expected counts, right? So just a bunch of 9s this time. Okay. And then in the third list, another empty list, I'll move my cursor up to the name of the list, L3, hit enter. And you see the cursor there, L3 equals. I'm going to enter these observed minus expected squareds divided by expected. Now, so in parentheses, first I'll put the observed values. Now all the observed values were in L1, so I go second 1, minus the expected values. All the expected values were in L2, second L2. Close the parentheses, square it, right? And then divide this by the expected values, divided by, again, L2. All right, and look at what happens. See, I get these 5 values. 5 values here. The test statistic is the sum of all 5 of these values in my list L3. So if you want to find the sum of a list, let's get out of here. Go above the stat button, there's this list area. Hit second, then stat. Go over to math, and then you see number 5 says sum, hit 5, and you see the sum of. What do you want to add up? Now I want to add up the values from list 3, L3. And look, it gives me the same exact number, because it's what this was. It is what this test statistic formula was giving me. Alright, so that's another way to do it. Right? And then a third option is to actually run the chi-square goodness of fit test on your calculator. Hit stat, go over to tests, and scroll down till you see chi-squared goth. I think it's at D. Yeah. Now I know this is on the 84s, TI-84 plus, TI-84. I don't recall if the chi-squared goodness of fit test is on the 83. So I mean, if it's not, don't worry about it. I mean, you can still do it the other ways I showed you. But if you got the chi-squared Goff test, goodness of fit, you click enter on that, and then it asks you, what's your observed data? Well, that was down list L1. That's already there. What was your expected counts? The 9s, that was down list L2. That's already there. Now, if you're only looking for the test statistic, the degrees of freedom doesn't matter. It'll give you the test statistic. But if you want the proper degrees of freedom for a goodness of fit test, you'll see this in my other video on running a goodness of fit test, completing all the steps. You take the number of categories, which is 5, right? There are 5 categories here. Take the value of k and then subtract 1 for the degrees of freedom for your chi-squared distribution. Right? So degrees of freedom will be 4 here. Again, it really won't matter if you're only looking for the test statistic. And then I go calculate, and you see that at the very top, chi-squared is 3.7778. It gives you the test statistic. And then below that, it also gives you the p-value, which will be the area to the right under the chi-squared curve of the test statistic. But again, that's not important to us right now. We're only looking for the test statistic. So no matter how you did it, by hand, with that adding up, going to the lists and doing that math on the list, the sum of a list 3 values, or just using the chi-squared goodness of fit test with the observed list and expected list, either way you're getting 3.778, and that's what I'll enter, 3.778 for our test statistic. Wonderful. And again, look at they're doing it the long way, right, by hand, like I showed you. And yeah, great. All right, so again, hopefully watching me do this either by hand or with the lists on the calculator, looking at the more instruction in Newton, reading your answer explanations when they come up. I'm hoping all this stuff helps you out when you're trying to do this on your own. And thank you very much for watching.